Hi. Hi. All right. That is a that is a that is a strong start. Oh my God. All right. I can't even do that. I feel like I have to run for president today. Okay. That is a strong start. Awesome. In fact, yes, I'm gonna do it out of no, I'm gonna do it in order, but okay. Long time no see. Oh, and she wins on both. Oh, not that it's a competition, but yes, right. Hi, Maisha. Good afternoon. Andrew. Hello, and good afternoon, Jessica. Oh, and wait, someone else is here. Wait, oh, many people are here. Okay. Hi, Maisha. Good afternoon, Andrew. Hello, and good afternoon, Jessica. Good. Oh my God. Good afternoon, Athea. I'm not even sure if she's talking to me, if she's including me when she says that, but good afternoon, Wishi. Where is her? Oh, I see her. Okay. Good afternoon, Manoj. Hi, Michaela. Good afternoon, Eric. Hello. Oh, Nicholas. Or Nick. Good afternoon, Zimin. Hello, Moticon and Leslie. Hello, and good afternoon, Alona. And someone else is here. Wait, I'm sorry. This is a big class, actually. Yeah, it's 10,000 big. No, just kidding. Okay. Oh, wait, well, good afternoon, Lynn. Hi. Oh, now this is where it gets weird. Okay, this is where it gets weird. Hi, Maisha again, and Nick, and Atia, and Leslie. Good afternoon, Catherine with a K. Hello, and good afternoon, Ruby with an R. Hi, now this is where it gets weird again. All right, we have something for this. I have something for people here, you people in particular. Okay, I'm going to say hi to Maisha again. I might regret it. Oh, here we go. Oh, now Nick. Oh, this is all. Yeah, okay. And then it's a he, so it's in third person. So good afternoon, Maisha. She's like the sophisticated one. I mean, not that the rest of us aren't sophisticated. Okay. Oh, now it's getting crazy, right? I see there's 18. I'm in trouble now. All right, wait a second. This is just unfair. I'm going to switch gears for a second. For a second, I can accept the check. Oh, I can scroll. Oh, okay. Oh, okay. Quick thing. Wait, sorry. Direct chat. I'm not mentioning any names or anything. If anybody emailed me, I am these days. I'm strangely good about checking email. If anybody just emailed me, then I don't know about it yet. But if you emailed me like within the last day and I didn't respond, I'm just saying to anybody, just in case there might be a direct chat about this. And the email that is best, weirdly, I know the best email to use for me is my official John J one, like the jj.cuny one. So I'll check again right after. If it was just, and maybe direct chat person even maybe wants to tell me. If it was like 5 minutes ago, then I don't know yet. But if it was like a day ago, then I think I didn't see it. But anyway, okay. Oh my God, Nick. Okay, that's funny. All right, Nick is really paying attention, and I have responses to that. But okay. I'm trying to learn how to scroll through the chat. That's got to be a thing. Yes, all right. Hi, Lisa, and I do agree with Althea that you all are looking lovely today, which all right. Okay. We're gonna do that's weird. Okay, all right. Very immaculate. Whoa. All right, I got the acceleration joke, and I'm gonna use that. Oh, 28. All right, now you're messing with me. Okay, you're messing with me today. Hang on one second. Actually, I'm not going to do anything weird. Well, I'm sure I am. But, okay. Okay. Wait. I don't know why I'm taking this so serious, but if there's an email to, I'm a little because I do want to take email seriously. And I kind of do these days. So I don't see anybody knows what I'm talking. Maybe send it again just in case, or definitely. Well, actually, I'm just going to put the best email address in the chat right here. This is not for 11,000 people. This is for just to make absolutely sure, because I know there's two flying, because there's one in the Google Classroom is different. But all right, just in case. But I am. Whoa. Okay, thank you. All right, direct type person, thank you, I appreciate it. I'm not trying to be weird, but I do want to take that seriously, so, okay. 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 And someone's in the waiting room, that's a good distraction. It's okay. And let me also say, I'm going to do this other thing, not just because you're overwhelming me with the chat, but I do want to specifically say, hello, Mark, hello, Ruby, hello, Michaela, hello, Zeman, hello, John. Hello, thank you. That's awesome. Hello, John. Hello, Manoj. Hello, Catherine with a K. Hello, Starnisha. Hello. I know some of these sound redundant, but there's a reason. Hello, Nick. Hello, Jessica. Hello, Andrew. Hello, Alona. Hello, Maisha. Hello, Jaylene. Hello, Athea. Hello, Mark. Oh, I said Mark. Okay, now I'm being, just because again, like really, the older I get with this, the more it's like amazing to me how many of you like really are really here, like with the video and everything. And again, those of you who are not, it's not a criticism or shaming thing. It's totally understood. In fact, that's actually why I praise the videos and the faces so much, is that honestly, like I think it's really hard. Like I'm in a lot of faculty meetings and stuff like that. And believe me, like the temptation to turn off my camera is overwhelming, to say the least. So, and then, you know what I'll even say, all right, really quick, I'll even say this about the whole thing about video and showing video and stuff. You know, the other thing about why I keep praising it, and again, really, it is not to shame anybody who's not doing it, because it's totally an option. But I think the other reason I keep making a big deal about showing video or showing faces or whatever during Zoom is because I also know that once class gets rolling, or once we get into anything and we're doing stuff, or at least I find as me, if I'm in faculty meetings or other things and I'm in a Zoom and the Zoom goes on for long enough and it's like substantive enough, after a while, I'm kind of like, why the heck is my video on? Like, what good, like they're only, you know, what good is this doing anybody? Like no one's like, should be paying attention to me because they're paying attention to the speaker of the meeting or whatever. And like, I keep seeing my own face and it's so distracting. So like, there's a definite thing after a while where it's like, is this even doing any good? Like, what is the point of this? I mean, I could, and I don't even know exactly, but I feel like, so the fact that anybody keeps it on at all is just so, it's like, it's such a gesture of good faith. Okay. Anyway, we do have to do class. We haven't had class in a long time. Remember face. I don't even get that, but okay. Okay, I sort of do. Okay, and speaking of acceleration, right? Oh, not that. Well, yes, that. Speaking of acceleration, oh, well, that is definitely true. Wow. The thing that Maisha just put in the chat, I don't even talk about playing with a. Yeah, no, that is really true. Wait, do I even, part of me really wants to go down that rabbit hole. But yeah, I mean, yes. So yes, in every possible way. And yes, okay. I'll just say that. Good point, Maisha. That is very true. That is true. Yes. Okay. What I want to talk about is physics. Okay, I also want to talk about YouTube, but I really want to talk about physics, especially because we didn't get to talk together last Wednesday. Supposedly, in principle, you watched the video last Wednesday of me going over a bunch of stuff, particularly in homework 4. Hopefully you did watch it. Hopefully if you didn't, you still realize that you still could, and it would still help a lot. But where I'm going to pick, so I'm not going to repeat everything from last week, but I'm going to pick up from what I want to talk about here. It comes from the very last problem on homework 4. I am going to repeat the contents of that problem. I don't think I'm going to confuse myself with a different screen share at the moment. I'm just going to sort of remind you all what was going on in that, you and 10,000 other, 11,000 other people, what was going on in question 4. No, excuse me, of the very last question of homework 4. what it led to was a new equation. That's the thing. The thing is now, to be as clear as possible, we are now up to equation number 3 in this class. And indeed, we are going to start accelerating. Like, indeed, I'm a very big believer in fundamentals. Like, the more we can really, really believe in and get what's going on the fundamental level, then the faster we can go when we need to go faster. And the more we'll be able to go ourselves and figure things out if we really know what we're talking about at the ground level. So far, we only have, so far, we had 2 equations spinning for a while. And we just, in theory, last Wednesday when I wasn't with you, in theory, I introduced the third. I want to talk a lot about it today. I wasn't with you, so I do want to actually try to make it as clear as possible. The third, but just to be concrete, the third equation, what it is this equation written in the middle of the page. I'm going to tell you where it came from in a minute again. I'm going to tell you how to use it. But first, just to read it in English or whatever, this equation in the middle of the page says the average velocity, double equal sign, like not triple equal sign, double equal sign, V naught plus V over 2. In English, average velocity equals initial velocity plus final velocity divided by 2. I'm going to write that a number of different ways. I'm going to break that down a number of different ways. But if nothing else, just notice this is our second equation. We only have 3 equations, right? And now out of those 3, 2 of them are about average velocity. If we're not careful, it could almost seem either redundant or contradictory. It could certainly seem confusing. If we only have 3 equations and 2 of them are about the same thing, that can almost seem silly. So I do have to spend some time showing you the distinction between the 2, like how they're used differently, how they mean something differently, blah, 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 blah. But also just to translate. So again, though, this equation in the middle of the page says average velocity is the first velocity plus the last velocity divided by 2. And remember, initial velocity is V naught, right? Like anything with the subscript 0 after it, anything naught means the value of that variable at time equals 0, right? I mean, that's what that V naught is. It means the value of velocity at the very first moment of time. The other velocity is any other velocity at any other moment of time, particularly the last moment of time. In other words, this is saying take the velocity when you're first paying attention, take the velocity when you are last paying attention, when you the end of the segment of some time, add them together, divide by 2, and you get average velocity. Now, before I go any further, notice that the velocities on the right side of this equation are 2 types of instantaneous velocities, right? They are referring to velocities at particular instants of time. We're still in a zone here where I'm not claiming we've never gotten an equation to figure out instantaneous velocity of time for all time. We had one homework problem on it, and I'll go back to that and talk more about it. But right now at this moment, right now at this juncture, I'm assuming that we all have an intuitive life experience sense of instantaneous velocity. Like, again, I think I babbled about this for a long time last time, but like, again, when the cop pulls me over and says, do you know how fast you were just going? He is not, or she is not asking me for, on average, in general, for the past hour and a half or 3 weeks and a half, how in average I was going. Like, that is not what the police person, what the officer of the peace is asking when they pull me over, right? They don't want me to say, oh, well, that's interesting. That's a really good question, officer. I mean, I've been traveling for like 3 days on this road trip, and although I did take 4 pit stops, like get gas once, go to the bathroom twice, and then like, you know, do weird things in the right lane for a while. Like, I only actually covered a total of 15 miles. Oh, and I backed up a couple of times too. So in total, I covered 15 miles for this 3-day road trip. So I guess on average, my velocity is 15 divided by 3, 5 miles per day, sir. Is that a problem? Like, no, like, yeah, that is a problem to say all that, besides the fact that I just bored everybody crapless. Like, That is totally not what they're asking, right? And all the physics we have done so far has been about average velocity or even then average acceleration. But there is a thing. What? Oh, so yeah, I knew that was going to happen. Sorry. By weird things in the right lane, I didn't really mean that weird. I actually meant like slowing down to like incredibly like incalculable speeds or even backing up and not putting on your blinker. That's what I meant. I don't know what weird things I meant in the right. I knew I was going to get in trouble for that. But my point is, oh my God, what? Well, because you can't do weird things in the, because, okay, you really, because I'm already being pulled over, right? So clearly I'm going too fast. So I'm in the left lane, obviously going too fast. But what I want to try to convince the cop is that I was doing all these slow things to average out the number to make the number lower than he thinks or she thinks it is, right? So I was trying to invoke the right lane as like I've been going a lot slower in general than you think, sir or ma'am. That's what I was thinking. I promise. Oh my God. But yes, I'm sure weird things can happen in the left lane. Oh my God. Oh, and people are trying to come in. Thank goodness. But thank you for paying attention to exactly the part that makes no sense. What I'm really trying to say, okay, now I am. Yeah, no, dude, can you imagine how bad I am at no, I'm okay. What I'm really trying to explain right now, I still can't believe that someone in this room had the audacity to describe me as having ADHD. I mean, completely true, but like, and I probably even said it, but still, Lord. Light bulb, fish, left lane. Oh, my point in the police example is that even though all the physics and all the equations that we have thus far are about average velocity and average acceleration, which very specifically are numbers meant to apply to a region of time and space. Like, here's the serious point, right? There is a concept of going at a certain speed, not over a region of time and space, not how fast you're going between a beginning and an end of some journey or some interval or some segment of time and space. There's a concept of like, how fast are you going right now? Right. And that's the thing that the police officer is really asking about, like whether or not they could actually really figure it out or no. Interesting question. But when a police officer says, do you know how fast you were going right then? They literally do. They don't want an average. They do not, they are not interested in over time and over space, one number being divided by another. They're interested in how fast were you going at that instant of time, right? Like, and we can all picture that right now, the car's going so fast. Now that is called instantaneous velocity. I want to stress again that that is a big part of physics. And instantaneous quantities are a big part of physics. And they are what's being denoted on the right side of this equation. This equation in the middle of the page is saying average velocity is the sum of a couple of different instantaneous velocities, like your velocity right now plus your velocity right later, added together, divided by 2. On the left of the equation is an average, like a bar over the letter. On the right is 2 instantaneous quantities. You could tell they're instantaneous because they don't have bars, like they don't have lines on the top of them. I want to stress again, they are real ideas. Instantaneous velocity is a very real, important idea in physics. It means velocity at an instant. We don't have an equation for it yet. There's a reason for that. I'm not claiming that we have a mechanism by which we can always figure it out. I'm just claiming that we know what we mean by the idea. And sometimes we can figure it out, or sometimes we have enough information to know it. And therefore, we sometimes have numbers to plug into this right side of this thing. Wait, I'm just going to look at the, okay, so an initial, whenever anybody says, in fact, I think this is the next page. Yeah. So going to the next page now, or it should flip in a second. What I'm saying is, this looked like, yeah, it looked like a legitimate question there, child. I'm looking, wait. Yes, as a good question, John. Yeah, all right, good point, Nick. Very good point. And that, I always have the audacity. Yes, you do. Yeah, that is true. Oh my God. Okay, that's funny. Next class, how to evade tax. Oh my God. Okay, that is very funny. And Althea's thing is very funny. And Nick's thing is very funny. And John, yes, and I'm getting to that eventually. If I ever do get back on the path, yes, I'm getting to what you're saying, John, in the chat. Yes, you can use the kinematics equations to figure out instantaneous velocity, depending on what information you have. Yeah. What I'm saying right now, I always have the audacity. What I'm saying right now, that totally should be the name of a movie or now. Yeah, well, I mean, someone's got to, I mean, right, someone's got to make this. Yeah. Okay, look in the page, please. Notice we have 3 equations so far for this whole class. Notice that there's a pattern that tends to be the case on the left side is some sort of quantity that is an average quantity that refers to the average between 2 endpoints of space and time. Then on the right-hand side of each of these equations are actual quantities that refer to actual moments or points in space and time. Like on the, either a position in space or another position in space. And yes, we have this ongoing pattern of like X's and X naughts or V's and V naughts or V naughts and V's. Please understand V naught or X naught or whatever always does. The naught thing means the very first value of that variable. If you don't see the naught there, and you don't see a bar of it, then it means any other value of that variable. But presumably, logically, usually it means, just like V naught means the very first one that you measured, if you don't have a naught, if you don't have that 0 subscript after the letter, then it generally connotes the very last quantity you measured. So what I'm saying here is this new equation that we theoretically got at the end of the last video, this new equation, that says V bar equals V naught plus V over 2. There's other ways you could write it, and you'll find in textbooks, like over here in the corner in black or brown or whatever. You notice it could be written V bar equals V initial plus V sub I plus V sub F, meaning V initial plus V final. Or it could even be written V bar equals V1 plus V2. I mean, all divided by 2. It doesn't matter what you call these two V's. The important on the right-hand side of the equation, the important thing to understand is that both of those two V's on the right-hand side of the equation are both instantaneous V's. V initial is one type of instant, like, I guess what I'm trying to say is sometimes people get confused at this point in physics where they think, oh my God, we have all these different kind of velocities flying around. Like there's instantaneous velocity, there's initial velocity, there's final velocity, there's average velocity. What I'm trying to say is no, actually there's 2 different types. There's average and there's instantaneous, and all the other subscripts and all the other different versions of velocity that sounds like we're talking about are all just different. They're just different examples of instantaneous, whether it's initial or final or first or last or middle. Those are just velocities at various points in some experiment, and V bar is the average for the whole thing. All right, so hopefully that clears up. Oh, yes, yes.
Unless we're being told to find instantaneous, are we supposed to assume that it's average we're looking for?
That's a very good question. That's a very good question. So, okay, my short answer is yes. And my long answer is yes. No, that's so obnoxious. My short answer is yes. I mean, and here's a slightly long answer. I mean, generally speaking, as to know which one to use, I mean, this is kind of what I do want to get into today, or as to know which one to use. Usually the English should give some keyword that makes it clear. Like if someone says something like how fast is something going at the 3rd moment, or how fast is something going right at the middle of the journey, or how fast is it going at the end of the journey, then all of those things do connote certain times. So for all those kind of contexts, you should assume we mean instantaneous velocity. So actually, you know what I'm really saying to Mark, and it is a great question. In a way, what I'm saying to Mark is, if someone's asking a question about velocity, unless they actually use the word average, you probably should assume they probably don't mean average, unless they actually use the word average. Again, like the police, and like all jokes aside, like the police officer pulling me over, when he says, do you know how fast you were going? Like, he's not using any words at all to make it clear. He's not actually saying average or instantaneous, but really, he does not want an average. He wants to know. He's asking, how fast was I going at a certain moment, like when I passed his car or her car. So on the one hand, and again, though, this is a very important question, and I am about to be more specific about it, but on the one hand, what I'm saying to Mark and everybody is if the English doesn't seem to make it totally clear, or the problem that's expressed doesn't seem to make it totally clear, then actually probably you're not being asked about an average most of the time. You're probably being asked about an instantaneous, and you probably shouldn't assume average unless you hear that word. But so okay, that's answer number one. But here's really why Mark's question is such a good question, or here's really what I want to get into today is, yeah, which equation do you use when? I mean, in a way, I think that's part of what Mark is asking. Like, because if you look, we have three equations now. We have three equations, and two of them are about the same bloody thing. I mean, like this one is about average velocity, and this one is about average velocity. So if we're not careful, it could be very confusing very fast. Like, which one do we use when, or how do we know which? And here's why I said yes initially to Mark's question. Notice that the first two equations we got during this year that we've been spending so much time on are triple equal sign. They are definitions. That's super important. The top equation for average velocity is the definition for average velocity. That means if it ever makes sense to you at all, if it ever makes any sense to you at all, if it ever seems at all true, then it's always true. And that's what it is. It's always true. Like, that first equation is not something anybody figured out in a lab. And it's not something that anybody's ever going to unfigure out in a lab. It's never going to be wrong if it is ever right. The top equation is just saying that what we mean by average velocity is how far something goes in a particular direction per how much time. It literally is just saying that's what we mean by average velocity. So it's always just, so it's like saying, it's like saying, oh, squares are four-sided shapes. Yeah. Or like, every square I see is a four-sided shape. Yeah, that is always going to be true because of the definition of squares. Like, you're never going to do an experiment to prove that wrong. So what I really want to say emphatically to Mark's question and to everybody else is, if you are doing homework or doing an exam, did I say that? If you're doing an exam, or like you're in real life and any of this comes up, if you have a problem with anything to do with velocities at all, the first equation you should always write down is that top one. That top one will always be right no matter what. At worst, you might find out in a beat or so that you don't have enough information to fill it in and get what you're looking for. Like, maybe you don't have, like this happened to us on the hill figure problem. Like, hill figure was all about average speed or average velocity. And the first thing to write down that we really should have written down is, okay, all we knew at that point, average velocity equals displacement per time. So we wrote it down. Then if we're like most people, we then look and we're like, okay, displacement would be like how far up the hill. Oh, Yavrabam didn't tell us the size of the hill. Like, I don't know the size of the hill. Now I'm screwed. Now what should I do? That was a challenging moment in the problem. The problem is that then what people started doing then at that moment is making up other equations that didn't exist, or making up concepts that were wrong, when in fact we should have done something else. But here's my point. If you write, the truth is that equation was the right thing to write down, even though we didn't have all the information, even though we had to keep thinking more about where to get that other information. If we wrote it down, it was the correct first way to start. I mean, the first step to starting. And if it were an exam, and I'm saying this seriously and as clearly as I can, if we're talking about velocities at all, writing the first equation down first will get you points. Like, to be blunt about it, you will get points for that, even if you don't know what to do past that point, even if you don't get all the points for the problem, because it's literally true. It's definitely true. And presumably it's somewhat relevant. Even if it doesn't solve all your problems, it's true. Now, the second one is where I want to, the one that in theory just got introduced or discovered at the end of the last video. And again, I will try to unpack it more today, but this second one, first thing to notice about it, and look, again, maybe it makes sense to you. I don't mean the second, I mean the third one, the second equation about average velocity, our newest equation. Whether you think you totally get the equation or not, and I think people probably think both things, Notice it's a double equal sign. It is not a triple equal sign. It is one of the reasons we didn't get this equation first is because it is not always true. It is literally only sometimes true. It's not a definition. It's like a discovery. It's a recognition under certain conditions of two things that can be equivalent. So first and foremost, again, this isn't exactly like, I know what Mark actually asked. He actually asked, like, should we assume instantaneous velocity or average velocity when, when it comes up and it's unclear? And hopefully maybe I've sort of answered that question, but I also want to go a step further because we now have two equations for average velocity. And it's very fair to ask, like, how do we know which one to use? And I'm saying first and foremost, always use the first one. The second one, notice it says above it, it says, I mean, this third one, V bar equals V naught plus V over 2. Notice it says IF, oh, thank you. See, and I didn't even fish for that. Thank you, Mark. That is total closing conversation points. Thank you for saying that. I was dying inside and I didn't want to ask. Okay, yes, cool. And I will look at the other chat in a second. But please, everybody notice another piece of notation, just like triple equal sign means equal by definition and double equal sign means equal by discovery or circumstance or condition, whatever. IFF means if and only if. What we are literally, this third equation and the next two that are coming are double equal signs equations that are only true under certain conditions. The condition is spelled out right here. What the condition says is IFF, if and only if A equals A naught. Now, what is that? Like, that seems certainly, what that's saying, that's a common standard notation to say, if and only if the acceleration at any point is exactly what the acceleration was at the beginning point. That's what A equals A naught means. Like, there is information there. It's not a throwaway remark. Like A equals A naught means is shorthand for saying that the acceleration never changes, that the acceleration is constant. Okay, we could also talk about V equaling V naught. Like, if you have constant velocity, if your velocity is never changing in a certain situation, then we would say V equals V naught. Like, that can be interesting. That's like very nice, but it's not part of these equations. What I'm saying here is we are getting here at the bottom of the page the first of a number of equations that are in fact often called the constant acceleration equations. It is a constant acceleration equation, even though it doesn't say anything about acceleration in it, right? Like, I'm saying V bar equals V naught plus V over 2 is not talking about acceleration at all. It's just talking about a relationship among velocities. But this relationship among velocities is only true when velocities are changing in a constant way. That's what the A equals A naught thing means. That's what I'm trying to say here. I mean, that is not a simple concept. I'm saying that we're now getting into the realm of velocities changing. That's called acceleration. That's what the second equation in the middle of the page is saying. Like, average acceleration is defined to be change in velocity per time, meaning that from one moment to the next, your velocity is actually changing its value, maybe going up, maybe going down, or maybe turning, because velocity is speed and direction. So if you change your velocity in any way, either you change its magnitude or you change its direction, then we say you're accelerating. And that's equation number 2 there in the middle of the page. But then this discovery we make, which again, I will sort of try to unpack in a moment, we come to realize, you can accelerate, but there's different ways you can accelerate. For example, I can be going 10 miles an hour now, and then a minute later, I can be going 17 miles an hour, okay? And then another minute later, I could be going 47 miles per hour, okay? And then another moment later, I could be going 5 miles an hour. I could be doing something very spazzy because I'm in the right lane. And that would constitute acceleration, right? I was changing my velocities. Like, every minute I had a new velocity number. So I had acceleration. However, the acceleration was not steady in the example I just gave. Like, if I go 10 to 17 to 47 to 13 or whatever, you could calculate the acceleration in each one of those moments. Like, first I went from 17 to 47 in a minute. So I could say, oh, my acceleration changed, my velocity changed by 30 miles per hour in a minute. My average acceleration for that little interval was an increase of 30 miles per hour per minute, right? I could say that and that would be right. And I'd be using the second equation to say that. But then in the next minute, I did some other value of A. Like then I jumped up a much bigger number. I don't remember what my numbers were. Then I jumped down a number. So then my acceleration was negative. So in the crazy example I just gave, we have accelerations, but they're like a bunch of them. They're all changing. In other words, in the example I just gave, I'm changing my velocity and I'm changing the change in my velocity, right? In calculus terms, in the example I just gave, the stupid example I just said, like when your velocity numbers are bouncing all over the place, in calculus language, you could say, my position is changing in time. So I have a velocity that's known as the first derivative of position with respect to time, right? Like if you put these things on a graph, like the graph would have a slope, right? I have velocity, so I had a first derivative of position with respect to time. Then I also had an acceleration, like I had a change in velocity. So you could say that there was a second derivative of position with respect to time. And in the crazy example I just gave, those acceleration values themselves were also changing. Like first I jumped up by 30, then I jumped down. So you could say there was even a third derivative of position with respect to time. Technically, that's called a jerk. Technically, this is called a jerk. Right? So you could have these derivatives going on forever. You can have situations where there's change in change and a changing change. But we are interested in stopping the madness sometimes. What we're saying here is if there is velocity, i.e. if your positions are changing, like equation 1, and if there is acceleration, equation 2, if there is, so positions are changing, so we have velocity. Say velocities are changing, so we have acceleration. But if the acceleration is not changing, if the acceleration is constant, if like basically all of the weirdness stops on the derivative number 2 level, then we can figure out some interesting things about the velocities they hold as long as the change is not changing. Let me be, okay, so what in English, what we're saying, and I'm about to explain, again, technically I explained this in the video at the end, but I'm about to explain it now, but just to one last time, in English, what this last equation says in English, like the thin red pen written on top of it says, so I'm talking about the third equation, the one that we're like trying to unpack right now. It says sometimes under special conditions, the special conditions being constant acceleration, sometimes under special conditions, the average velocity is the average of 2 velocities. That's what this last equation is saying, right? No, and I'm about to turn the page. I'm actually going to look at the chat too, scared as I am. But this last equation, and I'm spending a lot of time on this equation because it's our first double equal sign equation. It's our first equation that is not always true. And it's our first equation that's true for reasons that are not just like definition. So this equation on the one hand is not always true, therefore we have to be really careful about it. But on the other hand, I can assure you that when it's true and when we are compelled to use it, it means that our first equation for average velocity wasn't good enough. We didn't have enough information for. So this becomes a very important tool in the toolkit. Like this is the first equation where you really have to make decisions about when to use it and how to use it. That's why I'm making a big deal out of it. And so in English, what this equation's saying, if you haven't already noticed, is it's actually saying that average velocity sometimes is one velocity added to another velocity divided by 2. In other words, 2 velocities added together divided by 2. In other words, averaging, right? I mean, this is weird. It's actually saying like sometimes you could do the very thing that Yaffer Brown was yelling that you couldn't do a month ago. Sometimes if you want to get average velocity for a whole, you can take a couple of velocities and average them together, like add them together, divide by 2, and you will get the average for the whole sometimes. But the very key point is like, when are those times and why do we do it and how do we do it? Okay, but that is what it's saying. It's saying, and so please don't memorize. People always get into like, they try to memorize these equations and then they're like, oh, I know that one of them has a T in the denominator and one of them has a 2 in the denominator, but one of them has a plus in the numerator and one has a minus in the numerator. And I get them confused and I put the minus over the T and then everything is, please don't try to memorize them. Just try to see that they actually kind of make sense. Like the first one is the first equation for average velocity is displacement over time, as in like miles per hour. So it's like position final minus initial position over time. That's what that first equation is saying. Is just that average velocity means displacement per time. But this last, right, so it's divided by time. This last equation is V naught plus V over 2, because we're not saying, because now we're saying literally average, like add together these two values and divide by 2. Like that's what it's at. So, okay, so why are we saying that? When are we allowed? And I'm going to flip the page and so you can look at this copy. Let me just look in the chat and see it. Also, I know someone just left, so that's not a good sign. Noodle, what? Okay, wait. The true 1%. Okay. Yeah, it depends on what they give you. Yes, thank you. Okay, it's a bones day. I'm not trying to. Noodle. Okay, I'm totally lost on the bones noodle thing, but I'll just pretend I understand. Oh, and someone's here. Sorry. Okay. Yeah, but what does that mean? I don't know what that means. What does that mean? It's a bones day. I'm so out of touch. Does that? Oh, you'll have to. I don't. Oh, that's helpful. Okay. Well, thank you, Althea. That. Oh my God, that's the kind of answer I would give. What? Oh, okay. Okay, well, I can agree with that. Wow, I'm so out of touch. I'm like the guy who's out of touch. What is going on? All right, I'm totally going back to all right. So okay. You realize I hope it's clear to, well, I know it's clear to Nick. Nick noticed, at least what you've done is I now have a TikTok thing, for God's sake. Like I thought I would never see the day. But you're making me younger, you people. I feel so much more in touch now. But okay. Yeah, no, and I don't know what to do with it, but I have it now, for heaven's sake. What? Okay, I'm so, oh my God. If there were medicine, welcome to the dark. Yeah, seriously. Maybe not yet, because I'm really scared. And also, oh my God. If there were medicine for what it is I have, I would take it, but there isn't, and I don't. And what oh my God. Oh, okay. I'm so. I don't want to laugh at anybody's mention of their own crying. This is really, all right. I'm going to go on just because this is what I do sometimes. Okay. What happened? Oh, okay. I'm very sorry to hear that. Okay. I'm going to take that bait for a second. At some point, we should all talk about stats. I feel you. I mean, yes, stats exams. No, I meant it in a helpful way. Okay, no, I'm totally going. I meant it in a sympathetic way, but okay. Okay, so look, what's on the board here? Yeah, I'm pulling it back. Okay, what's on the board here is asking you to picture what is in fact pictured at the end of the last problem of homework 4. Like you may recall in the very last problem of homework 4, there were like rows of numbers. And some of them seemed like they were in patterns, and maybe some of them didn't. And then you were asked to take averages of these numbers. Okay, so I want to bring everybody to this point again. I want to do this freshly with everybody. Like what it says here on the board is picture a set of raw numbers. Like just a simple set. Like it could be like the numbers 1, 2, 3, 4, 5, 6, 7. It could be the numbers 1, 3, 5, 7, 9. It could be random numbers like 1, 1, 1, 1, 1, 2, 7, 2, 7, 2, 7, 9, 4. Like whatever. Yeah, that's it. Oh, was it homework 5? I'm sorry. Maybe it was homework 5. I thought it was homework 4, but maybe it was homework 5. I'm sorry. But yes, there was definitely a problem at the end of a homework assignment where there was like rows of numbers, and you were asked to take averages of them. And I'm partly tempted to pull up the thing right now, but I think I'm going to get very distracted if I do. So just picture a set of numbers in your mind And I'm going to give you an example in a second. But now, so the example I'm thinking in my mind is the numbers 13579. Okay, the numbers 13579. Now I'm asking you to picture that each one of those numbers represents like an instantaneous velocity. So, I mean, I'm just picturing numbers because I sort of feel comfortable, like I sort of know what numbers do sometimes under simple conditions. But in the back of my mind, I'm picturing like when I say 13579, what I'm really picturing is like 1 mile an hour, 3 mile an hour, 5 mile an hour, 7 mile an hour, 9 miles an hour. Okay. And I'm picturing that it's like what some car or something is doing. Now I'm going to go a step further. It says in the sheet, right? So each one of those numbers is an instantaneous velocity, a velocity applicable to one moment in time. Then what it says at the bottom of the sheet is picture an equal time interval between each pair of raw numbers. So it sounds very complicated. I'm not trying to be complicated. I'm just saying, like, now I picture that it's like 1 mile an hour and an hour elapses. Then 3 miles an hour, then another hour elapses. Then 5 miles an hour, another hour elapses. Okay. So what I'm really trying to get at is what we're really imagining. It's like a table of values almost. It's like we've got some object like a car or something, and we're taking measurements at equal time intervals. It's like time is the independent variable. It's ticking on in a regular independent way. Like I want to see how fast the car's going right at the beginning. Then I want to see how fast the car's going an hour later. Then I want to see how fast the car's going an hour later from that, and then an hour from that, right? So I'm like jotting down like 0th measurement, 1st measurement, an hour in. Okay, sure, cool. Okay, cool. So thank you. I appreciate your honesty. Just closing a conversation. And someone's coming in the door. Okay. So picture yourself at equal time intervals taking velocity measurements for some object like a car or something. And so in the left column, you're writing like hour 1, hour 2, hour 3, hour 4, but they're all even. It's not supposed to be a trick. And then in column 2, you're writing down those numbers that you found. So if I picture in my mind the set of numbers 13579, I'm imagining what that really means. It's like readouts. It's like speedometer readouts or radar detector readouts that came at equal time intervals. 1 mile an hour, 3 miles an hour, 5 miles an hour, 7 miles an hour, 9 miles an hour. Okay, so that's what we're picturing. And you can picture whatever numbers you want, but just picture that that's what they mean. Then what I want to say about that, what we sort of in principle discovered at the end of homework, I guess it was 4, and what in principle I discussed in the video, but whether or not you saw the video, what you sort of notice is what you notice is if the numbers are in a certain kind of pattern, in a very certain kind of pattern, then it's really easy to take averages of those numbers. And if the numbers are not in a certain kind of pattern, it's not so easy to take averages. In other words, take the numbers 13579. If someone asked me to average all those numbers, well, certainly what I can do is the safest thing, which is I can add up all the numbers together. 9 plus 7 is 16. 16 plus 5 is 21. 21 plus 3 is 24. 24, no problem. Got it. Thank you. 24 plus 1 is 25. Right. Okay. Right. And there's 5 numbers in total. So I add them all up, I get 25, I divide by 5, and I get that the average is 5, right? Like I can always add numbers up to get an average. And if the numbers were not in that pattern, even if they were in the numbers like 1, 1, 1, 1, 2, 7, I would add them all up and divide by the number of numbers. But the thing is that I just added up all those numbers and I got that the average was 5, right? So keep your eye on the prize here. The eye is like we're trying to average. The thing is, as long as those numbers were in that kind of a pattern, as long as the numbers were always increasing or decreasing by a steady amount, right? Like I went 1, 3, 5, 7, 9. I could have gone 9, 7, 5, 3, 1, or whatever. But notice I was just always stepping up by 2, right? And there's nothing special about 2. It's just that it's some number. Then the interesting thing happens where I say the average is 5. And I step back and look at those numbers and I'm like, did you say the average was 5? You said when you add up 1, 3, 5, 7, 9 and divide by 5, you get 5. Well, that's interesting because 5 is the number right in the middle there, right? 1, 3, 5, 7, 9. The average, adding all up and divided by 5 was 5, but 5 also happens to be the number right in the middle. And I think to myself for a second, is that a coincidence? Is it just because the numbers are in a pattern? Well, if I'll tell you this, it's not a coincidence, and it is because the numbers are in a pattern, and it's not just any old pattern, right? Because again, if you did the homework, you'll notice I could put numbers into some kind of pattern, like 1, 4, 9, 25. Sorry. I could put numbers in a pattern like this: 1, 4, 9, 16, 25, 36. That pattern is called the perfect squares. It's definitely a pattern. But if you add up all those numbers and divide by the number of numbers, you're not going to get the middle number there. What I'm saying here, what we're saying is, if your numbers are always growing by the same amount or always decreasing by the same amount, in other words, if your numbers are always changing, but in an unchanging way, if they're always changing, but by a constant amount, as in 1, 3, 5, 7, 9, I just keep on adding 2. Each new number is a new number. Like the numbers are changing, but they're always changing by 2. If I do that, apparently averaging all the numbers up, adding them all up and dividing by the number of numbers will yield the exact same result as just plucking the middle number. Interesting. And it's not a coincidence, right? Like I said, and I'll do another, so do a different example, or let's do it. Oh, okay, wait, let me see this. This looks relevant. Yeah. Very good. Okay, John totally gets, we can make fun of John for actually doing physics in the middle of a physics class, which is this weird tendency he has. I don't know where it comes from, but that was total physics, and I'm kidding, obviously. But yes, so what he's saying there is exactly the point. This restriction of numbers changing in a constant way is literally equivalent to saying acceleration. And forgive me, I actually have to make a small correction to what he's saying. What he's saying is so relevant and so right on, but actually he's also going to get 11 points for it, to be totally honest. He's also going to get 11 points because there's actually one little aspect of it that's just wrong enough that I do have to say, and I mean this with total respect, and this is why. And he's going to triple dip that. He's going to get like points for making a claim. And here's the thing. If the numbers are always changing the same way, it's not that acceleration is 0. It's that A equals A naught. It's that acceleration is what accelerate. It's that acceleration is a constant. It's not that acceleration 0, because there is. See, if these numbers, but I'm really glad he's asking. And this is serious. And I'm glad, he's totally going to get points for this. Really. But let's be really careful about this, because this is a point. If you imagine those numbers 1, 3, 5, 7, 9 were, what is it? Yes, sweet. If you imagine that those numbers were 1, 3, 5, 7, 9, if you imagine that those numbers represent velocities at moments in time, so it's like 1 mile per hour, 3 miles. Let me be even more specific. 1 mile per hour, then an hour later, 3 miles per hour, then an hour later, 5 miles per hour. Then what's happening there is the velocities are changing, right? If this is a car, it's getting faster and faster. Faux show. The car is getting faster and faster. It is accelerating. It has an acceleration, which isn't 0. And this is a part where I'm respectfully embracing, but disagreeing with part of what John said. If a car were doing this, we would totally say that it totally does have non-zero acceleration. Specifically, if these were all miles per hour and they were separated by hour intervals, I would say that that car has an acceleration of 2 miles per hour, or in other words, 2 miles per hour squared, right? Because first it was going 1 mile per hour, then an hour later it was going 3 miles per hour, then an hour later it's going 5 miles per hour. So it's gaining 2 miles per hour of velocity every hour. So I would definitively say, so this is an example of acceleration in action, right? The car would be accelerating at a non-zero rate. Like 0 acceleration would mean cruise control, just that you're always going 10 miles an hour or whatever. But this car has an acceleration of 2. It's just that. It always has an acceleration of 2. It had an acceleration of 2 at the beginning. So if we measured it, its acceleration, not like its velocity at the beginning was 1 mile an hour. But right from the start, we could see its acceleration was 2 miles per hour squared, right? Velocities in miles per hour. Acceleration is in miles per hour squared, like miles per hour. And we would say that this car had an acceleration rate of 2 miles per hour from the get-go, but it always maintained that acceleration. It didn't maintain a constant velocity, right? This is very tricky. We're saying there's we're saying that this car has an unchanging change. It has a change that is unchanging. It has a change that is constant. It has a acceleration that is constant. It has a changing velocity, but an unchange in the change in velocity. It's accelerating 2 miles per hour squared always throughout, right? I mean, what's really great about what John did, what's really right, is he totally sees the analogy that I'm making between raw numbers and velocities. And here's, now let me go further. What I'm saying is, in a case like that, if you're always gaining 2 miles per hour of velocity, or if you're always losing it, or if it's a different number, it doesn't matter what the number is, but if the number isn't changing, if the change in the numbers is remaining fixed, then the middle number is just as far away from the top as it is from the bottom. Like the middle is literally the middle, like not just the one that, like 5, put it this way, if I go 1, 3, 5, 7, 9, 5 is the average, not only because I added up all the numbers and divided by 5 and got 5, but if you think about it, 5 is the average because 5 is 4 off from 9. Like 5 could be the number that's used to represent the whole, because even though it doesn't quite capture that 9, like it's like 4 units lower than 9, like 5 is representing the whole. It doesn't seem to represent the 9 very well. It shortchanges the 9 by a factor of 4, but it also overchanged the 1 by exactly 4. The number in the middle is exactly it's above the bottom by exactly the same amount as it is below the top, because the numbers are always growing in the same rate, right? Like that wouldn't be true if I go 1, 4, and you could write this down if you want to test, or if you did the homework, whatever. If I go 1, 4, 9, 16, 25, right? Those are like perfect squares, right? 1, 4, 9, 16, 25. The number right in the middle there is 9. Like the middle number I mentioned was 9, but that is not the average. If I add up all those numbers and divide by 5, I'm going to get a number much bigger than 9, because the numbers are growing as they grow. So 9, that number in the middle, 1, 4, 9, 16, 25, 9 is like very far away from 25. In fact, it's 16 away from 25, right? But it's not so far away from 1. It's only 8 away from 1. It's not actually in the middle, just because you see what it's right. So if and only if numbers are growing by a constant rate, if and only if velocities are changing by a constant rate, if and only if acceleration is a constant, then we can say that the mean for a whole bunch of numbers, the mean, the average, the arithmetic mean, is actually the same as the median. This saves us a lot of trouble. This means now that if we want the average, which we often do for a lot of reasons, it says that even if we have a whole bunch of numbers, we don't have to spend time adding them all up and dividing by all those numbers in order to get the average. As long as we know that the acceleration is constant, we have this trick where we can get the median by just spotting where we can get the mean by just spotting the median. And wait, it gets even heavier if you look down at, so that's what the black part of the sheet in the middle is saying. But now look even further to the blue part at the bottom of the page. Let's go even further than that. Look at when I say 1, 3, 5, 7, 9, when I say that the average is 5, which is the middle number, also think about this, 5, 5, 5. 1 plus 9 is 10 divided by 2, 5. What did I just do? I just took the bottom number 1, the very first number, right? I added it to the top number 9, and I divided by 2. I pretended they were the only 2 numbers in town, 1 and 9, the lowest and the highest. I added them together, divided by 2, and I got 5, the middle number. In other words, wait a second. That middle number, which is the mean for the whole set, is, oh, thank you so much. Oh my God, thank you. is like, how can I even get it? Like, what if people didn't arrange all the numbers for me? You know, and like, what if I can't see where the middle is or something? What I'm telling you now is, in order to get the mean, you can just pluck the median. In order to get the median, you can just take the mean of the lowest and the highest. You can ignore all of the intervening values because, again, all the error that you think you do by ignoring all those numbers in between the lowest and the middle, well, you're equally ignoring all the numbers between the middle and the highest, and they're all increasing by the same amount. So you're off in one direction by exactly the same amount as you're off in the other direction. So what I'm really saying is, let's say we do the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way up to 99, right? But if we're always increasing in that pattern, thank you so much. If we're literally going like the numbers 1, 2, like 1 mile an hour, 2 mile an hour, 3 mile an hour, 4 mile an hour, blah, 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 up to 99. If I want to know my average velocity for that, okay, I definitely do not want to sit here and add up all the numbers from 1 to 99, even though there's a trick for doing that. But like, I don't want to do that. I don't want to add 99 to 98 to 97 to 96 and then divide by 99. That's crazy town, comma, yo, right? But what I could do is say, well, wait a second. They're always stepping up at it. You know, it's always 1, 2, 3, 4. I'm always just growing by 1 each time. Thank you. You really are paying attention. Thank you. Right. So what I could do is take the 99 at the end, the highest number, 99, add it to the 1 at the bottom. Thank you. 99 plus 1 is 100. Divide by 2, I get 50. 50 is the number right in the middle of 1, 2, 3, 4, 5, 6, 7, all the way up to 99. 50, you could check it on a calculator. 50 is the average of 99 plus 98 plus 97 plus 96 plus 95 plus 94 plus 93. Blah, 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 blah. All I have to do is add the first to the last, divide by 2, and I'll get the middle. That's like the third implication of this equation. That's what this equation is saying up at the top. I'm saying, okay, I am saying, if the board comes over, come on, what is it? Internet, modem, Lego. Okay, yeah. When it says V bar equals V naught plus V over 2, what it's really saying there, and we're almost, yeah, what it's really saying there is, if you want the mean for this whole set of velocities, you actually can get away with just plucking the median. You can actually get away with just plucking the median. And if you want to know what the median is, all you have to do is average out the lowest and the highest, because everything happening in between is happening in a steady pattern. So the average velocity for some region of time and space, some journey, is simply the average of the lowest velocity and the highest velocity. All you have to do is average out add together the lowest and the highest, divide by 2, as long as acceleration is a constant. It's saying if acceleration is a constant, then the average velocity is simply the average of the lowest and highest velocities. That is a major convenience. It allows us to do a lot, particularly in situations where we don't know the time or we don't know the displacement. Like, always, to bring it all the way back to the Marx thing, or sort of Marx thing, when in doubt, always use the other equation for average velocity first. But the moment you feel like you don't have enough information to use the other equation or something, number one, then see if you can use this. See if acceleration is a constant, in which case, and only in which case, you can use this. But last thing I have to say, so again, I have to warn you, this equation, the reason I'm spending a whole lecture on it, and I am, that's not an accident. This equation comes with the most decision-making, or this is not just a plug-in kind of equation. This is an equation that you use as a tool or as a technique or a trick to advance in a hard problem when at a moment that you might feel like you don't have a lot of information or something. And it says more things than just meets the eye. Specifically, like I'm saying this equation means the 3 things that I just wrote on the sheet. It means that the mean equals the median, that the median can be computed by taking the mean of the first and the last. Like that's two different ideas right there. But then also the third thing I wrote in black, and I'm promising you all right now, the third thing I wrote in black and then wrote on the side, I mean, I'll read it out loud in a second. It's pretty illegible, I suppose. It almost should be its own equation. This third thing I'm writing in black is like the most common way we use this equation, but it is so behind the scenes. Like it's the place where people get the most confused or the most surprised. What I'm really saying at the end, I mean in black, is what we're saying in the end is that as long as acceleration is constant, again, if and only if acceleration is constant, then the average for a whole set of values, the average velocity for a whole journey is the same number, the same numerical value as the instantaneous velocity right at the middle of the journey. By middle, I mean the middle of the time. Like, so what I'm trying to say, and this is very powerful. Again, this should almost be its own equation. I'm saying, well, I'll read the side thing in a second, but I'm saying again, please understand, average velocities and instantaneous velocities do not mean the same thing. They aren't the same thing. There's the average for a whole segment that applies between 2 points in space and time. And then there are velocities that exist at points in space and time. Right? Like what the cop is pulling you over for or me over for or whatever. They are different. They have different symbols. V average means V with a bar over it, and V instantaneous does not have a bar. They're for any situation where there's any acceleration at all, we're changing our instantaneous velocity all over the place, right? So we have many different instantaneous velocities if we are accelerating. So there is no reason to believe that any one of those at best, one of those instantaneous velocities would be average for the whole thing, but all the rest of them would not. I mean, again, it's just like if you're in a college physics class and you take a lot of exams, let's say, right? You get scores all over the place. Like you ultimately have an average for your scores, but maybe that average is the score. If you got a bunch of different scores, then at best, your average ever happened on one exam. All the rest of the exams are specific individual scores that are not the same as your average, right? If your scores are changing all the time. So same thing with velocities. We do not want to assume in general that the average velocity for an interval is the instantaneous velocity at any one point. However, this equation that we're doing now does say, well, there is one way to bridge between the two. Again, this kind of goes back to Mark's thing. I mean, I don't want to keep on talking about the same people over, but I do. But like, let me just look at the time. Yeah, I almost want to write this down, but look, here the real truth of physics is averages apply to regions between points. Instantaneous quantities apply to single points. The real truth of physics is that averages are always easier to calculate, easier to measure, easier to picture, and less precise. Instantaneous quantities are always more precise, more exact, more often what we exactly actually want, but they're harder to measure, they're harder to picture, they're harder to calculate. So there's always this dance between the two. And you might even want to write that down. I don't know. Like average quantities are easier to measure and less precise. Instantaneous quantities are more precise, but harder to measure. And just because you know one doesn't mean you know the other. But what this equation is saying is, as long as acceleration is constant, then the average for the whole, the thing that's easier to measure and the thing you can get from the other equation, the average for the whole, the displacement over time, will be the exact instantaneous velocity at one exact special known point. That point is the middle of the time, halfway through the time. Halfway, if your velocities are going 1 mile an hour, 3 mile an hour, 5 mile an hour, 7 mile an hour, 9 mile an hour, then your average velocity for the whole thing will be 5 miles an hour. And that's the speed you're going right at the middle moment of that accelerated journey. So what it says on the side of this sheet here, what it says right here is, it's an implication of this last equation. It's not its own equation. It's like an implication, but you really should write it down because it's the thing that's always forgotten. It says V bar equals V, like V bar, average velocity equals instantaneous velocity at at t equals 1/2. Probably should say at t equals, I don't know. It should say t equals t over 2 or something, but it's saying the average velocity and the instantaneous velocity are one and the same quantity at the midpoint of the time. Average velocity is midpoint velocity. And that way you can usher back and forth between average quantities and instantaneous quantities. You can use the midpoint of something to do that as long as acceleration is a constant. That's what I'm saying. Okay, wait, thank God we do have 5 minutes, right? Yeah, we have 5 minutes. So I'm going to pause for a second. I'm going to look in the chat, but let that sink in for a second. Okay. Oh, yeah, let that sink in for a second, please. Because it is a big. In fact, wait, I'm going to do quick. Yeah, actually, I'm going to do a really quick. We have 5 minutes. I'm going to do a quick. I feel like that was so much talking. I want to do a really quick. This is a concrete, fresh example. It'll take us 3 minutes to do, but just an example to make clear what I'm saying. Okay. Now I know we only have 3 minutes and 2 minutes. I'm going to respect that. This is a really important exercise to write down or get later from the note. I think we could do this in a minute and a half, but I'm going to, okay. Wow. Okay. Wow. Okay. Okay. All right. I'm going to do this because really I'm babbling so much. I would like to pray that this is actually a clear point in the end. So look, we have a car that accelerates at a constant rate of acceleration, like at a constant rate of acceleration, a equals a naught, okay, from rest for 10 seconds. So we've got a car that starts parked and it starts speeding up, but at a constant rate. So it's getting faster and faster and faster, but in a steady way. And it does it for 10 seconds. During that time, it travels 80 meters. Okay. Now, what I want to know is, and I know we only have like a minute and a half, but the question here is, what is its instantaneous velocity at t equals 10, like at the very last moment? Now, if I had more time, we'd have a whole big discussion about this. And I think a lot of people might actually say some really thoughtful, interesting, good things, but they'd be wrong. I mean, some of them, because I want to know how fast it's going at the end, at the 10th second. So let me tell you right now, the answer is not 8 meters per second. Right? If your first instinct when you look at this, and again, even if I'm going too fast right now, or even if you can't think this fast, please at least write this down and sort of think slowly about this later, or like relook at the notes or relook at the video. Just listen or just check it. You'll check it for like 60 seconds. Something goes 80 meters in 10 seconds, but it's speeding up the whole way from rest, right? If your instinct is to take 80 meters and divide by 10 as your first thing to do with this problem, that is the right thing. Again, this goes back to the mark point. If you don't know what to do, or you don't even know what I'm asking, but your first thing is you want to divide the displacement by the time, good thing to do. Go for it. Yes, divide 80 by 10, get 8. Now ask yourself, what did you just do? You just got the average velocity for this whole thing, the average velocity for this whole thing would be 8 meters per second. That is not the answer to the question, because the question's asking how fast is the thing going at the 10th second. If you divide 80 by 10, you get 8 meters per second. And I'm watching the clock, I promise. You get 8 meters per second is the average velocity for this whole thing. What does that have to do with instantaneous velocities? What our entire lecture today is trying to show is that that would be the instantaneous velocity right in the middle. The average velocity would be the middle velocity, right? It started from 0, it'd be going up, it'd be going up. It would reach 8 meters per second at the 5th second. And then it would keep going faster and faster and faster, right? By this, well, yes, they're totally correct. I'm not actually saying that right now. You could totally use that. That is correct, but I'll get to that next class. You don't need that. That is correct, but you don't need that to see this. All you need to see is that average is middle. So the average velocity, 8 meters per second here, would, no, so I think the answer, really good, and you totally get points for that, but I think the answer would be 16 meters per second. The answer to this question, I'll just write it, and we can think, we'll pick up on this on Wednesday. But I think, see, it's simple, but it's not easy. I think the answer for V at the final second, at the 10th second, would be 16. No. Well, the middle would be 8, because 80 divided by 10. And again, the first thing that everybody wants to do is the right thing to do. You just need to know what it is that you're doing when you do that. When you divide 80 by 10, you get 8. That's the average velocity for this whole thing. Well, this whole thing, we know it started from rest. It says in the middle, it started at 0. So its lowest velocity was 0. It's steadily increasing until it reaches an average of 8. But if that's its average, that can't be the highest number it ever gets, right? I mean, not like there's got to be numbers higher than that if that's going to be the average. Oh, good. Okay. So I'm just saying to everybody, 0, blah, 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 8, blah, 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 16, so that it makes the average 8 and the final thing is 16. Let that sink in. And it's not meant to be tricky. It's just meant to be the punch, like the conclusion example of everything we're saying today, but it shows you the importance of the training. I'm going to shut up. You are a very, very good class. I really appreciate you. I'm stopping, but you can stay to ask any questions. I mean, I'm not going anywhere, but you can go. Thank you so much. And yes.
Have a good day.
You too. Thank you very much. Okay, I'm stopping the recording. Okay. And yeah, we will go over it next. Absolutely. I'll pick up right there from next time. But please do like let it sink in or think about it. But yes.